In this video, we're going to review the concept of diffraction. Diffraction is what happens when a wave passes through a narrow opening or past a sharp edge. You can think about this like waves from the ocean entering a bay or a harbor. If the entrance to the harbor is large compared to the wavelength of the waves pass primarily straight through, and there isn't much effect. Near the edges of the harbor, though, the waves get bent. If the harbor entrance is very small, then the effect is larger and in fact becomes dominant, and you see the waves spreading out. In fact, if you send a row of straight waves towards a small opening, an opening that's much smaller than the wavelength, then on the other side of the opening the waves will be circular in shape. So the amount of the spread depends on the wavelength primarily, and this is the concept that we call diffraction. Single slit diffraction is, as I mentioned, waves going through a single opening. In that case, the waves actually interfere with one another. So we've already talked about the double slit experiment and interference of waves there. And we've talked about thin film interference. Diffraction is a separate concept in that the waves are bent as they go through the narrow opening. But diffraction always also includes interference, so the waves will in fact interfere with one another. This is, again, as with the double slit, due to the path length difference between the waves where they begin going through the slit and where they end, or where we observe them. So here we have a slit with waves coming through. As the wave comes through, it gets bent and travels in the direction of the blue arrows. So here we've called this wave 1 and wave 1 prime. The width of the slit we call W. And here, as you'll see in a minute, we've split this slit up into two segments down the middle and with even sizes or widths on either side, so each of these is W divided by 2. So with this pair of adjacent slits that we have, so instead of one slit here now, we can really imagine this as two separate slits right up against one another. We have now additional waves coming through. We can think of wave 1 and 1 prime, or 2, 3, 2 prime, and 3 prime coming through these slits with width W over 2. So for every wave we have up here in the top slit, we have another wave coming through in the bottom slit. So for wave 1, we have 1 prime, for 2, 2 prime, and for 3, 3 prime. We can think of those as identical waves, 2 and 2 prime, really as identical waves, but coming through the different halves of the slit. So if theta here equals 0, theta is the change in angle from the direction directly ahead, perpendicular to the slit, and the direction that the wave is bent in. If we think of theta as being 0, then for wave 1 and 1 prime, the distance to some screen off here to the right are even, as they are with 2 and 2 prime and 3 prime. So the distances are all the same, and so straight ahead, or at an angle of 0, we get constructive interference. We call this a bright central fringe. If the angle is not 0, though, then the path length difference between them is W over 2 times the sine of this angle theta. So yes, we are here going to deal with the trigonometry. We have to worry about the angles when we're talking about diffraction through a slit. So if you work out this distance, it comes out to W over 2 times the sine of theta, where we have a right triangle here, the hypotenuse of the right triangle is w over 2, and this side, the opposite side from the angle, is what we're interested in. That's the additional distance that wave 1 prime travels relative to wave 1 if they're moving off to some distant screen off to the right again. So there is some angle at which this path difference, w over 2 times sine of theta, will be an integer plus half of the wavelength. And at those angles we get destructive interference. So the angle then at which we get this destructive interference is related to the wavelength of light coming through and the width of the slit by this equation. So we take the path length difference, and in this case we're just going to set it equal to half a wavelength. And if we then divide or multiply through by 2, we get the width of the slit times the sine of the angle is equal to the wavelength. So we have this relationship between w, theta, and lambda. And notice we've denoted this as theta dark, so we get destructive interference at that location, or at that angle. This is symmetric around that midline, so if we have theta going up in that diagram or theta going down, it's identical. So there are dark fringes on either side of the bright central fringe. So here's an example of that. So once again we have these waves coming in. As they come through, if they go through straight with theta equals 0, we get our bright central fringe. If they come off with the right angle theta, related again to the width and the wavelength, to get this dark fringe, we get a dark fringe at the angle theta above that and at angle theta below. And here, as you'll see in a minute, we're going to define this width, the width of the central fringe, or the distance between the dark fringes, as this value s. So if we look at that width, then the width of the central fringe, s divided by 2, gives us then the distance between the central fringe and the dark fringe. And if we look at this triangle, then the length, if we call L the length or the distance to the screen, as we did with the double slit, then this side of the triangle is L, this side of the triangle is S divided by 2, and we have our angle theta, so we get the relationship S divided by 2 is equal to L times the tangent of theta. And it turns out for small angles that the tangent of theta is about the same as the sine of theta. And unless we have this screen very, very close, then these angles are going to be very, very small. So for any screen distances that are reasonable, we can make this approximation that tan theta is approximately equal to sine theta. And that helps us because we can also define sine theta as lambda divided by w. That's from our previous definition for the location of these dark fringes. Remember we said w times sine theta dark equals lambda. So here we've just rearranged that to find the sine of theta. So we have an expression for the sine of theta in terms of the wavelength and the slit width. We can just plug that into this equation. And so we get the width of the central fringe S in terms of the distance to the screen, the wavelength of the light, and the width of the slit. So we can say something about this central fringe. Or in many cases, for example, we may want to know how wide the slit is if we don't already know that. And so all we have to do then is set up a screen at some distance from a slit with an unknown width, put light through of a known wavelength, measure the width of this central fringe, and we can derive the slit width. And we'll come back to that in a few minutes. However, since the distance to the screen is somewhat arbitrary, we can really move this screen forward or backwards however we want. It's not going to change the physics of what's going on here with diffraction. We usually don't want to include that in the equation if we can help it. We'd like to come up with an equation that's independent of an arbitrary value like that. So we talk about the angular size of the central fringe. Really, that's just talking about what is this angle. So 2 times theta gives us the angular size of the central fringe, and that doesn't depend on L. And in fact, for these small angles, 2 theta is approximately equal to 2 sine theta. Once again, we substitute in for sine theta in terms of lambda and w. So 2 theta is equal to 2 times the wavelength over the slit width. So that gives us the angular width of this central bright fringe. And again, we can use that in the same way if we want to determine the width of some slit, some unknown slit. We put in light of a known wavelength, and we just measure the angle of the central fringe coming out. And in this case, please note that the resulting angle, that theta, is in units of radians, not in degrees. You'll need to keep that straight. Alright, so that is the first dark fringe. But if we continue to increase the angle, the path difference will change again, and we start to get constructive interference again. And eventually the path difference will be lambda. Remember, we started off going outwards, increasing the angle until we had a path difference of lambda over 2, where we got destructive interference. When we go past that particular angle, then we start getting constructive interference again. So we'll see another bright fringe showing up on the screen. And we'll continue along. Eventually, the angle will give us a path difference of lambda, or equal to a wavelength. It turns out at this location we do not see constructive interference, though. We get destructive interference. So we might think initially, well, if the path difference is exactly one wavelength, then those phases should line up again, and we should see constructive interference. However, if we think about it a little more broadly, we see that that isn't what happens. And to figure out why, we now imagine that we can split this slit up into 4 parts with width w over 4. So if we repeat our previous calculations, but now we have w over 4 as the width, we get this dark fringe occurring at some angle, theta, and now we get lambda over 2, again, because this is the phase shift for destructive interference. So where does that occur? Well, if we multiply through by 4, we see that we get another dark fringe, theta dark, at 2 lambda. So we see that rather than having constructive interference at that location, we get destructive interference from these imaginary sets of 4 slits. Remember, originally we started off with an imaginary set of 2 slits. For every wave coming through the top slit, there was another identical wave coming through the bottom slit, and we compared those. But now we look at it as 4 slits, and we see that if we split it up into 4 slits, then when the original path difference between those two is lambda, there's another set for each of those waves, another set of waves that give us a path difference of lambda over 2. So we've really just, as I said, split up this slit into 4 parts rather than 2 parts, and we get a dark fringe. It turns out we can do that with all sorts of combinations of slit widths. So we can split this up into 2, 4, 6, 8, as many of these pairs of slits as we want. It has to be an even number because we're always looking at pairs of slits. And that means we can take this equation that we got for 2 slits, and in this version for 4 slits, and we can generalize it to figure out where the dark fringes occur. And remember, before we just had W sine theta equals lambda. Here we have W sine theta equals 2 lambda, and if we generalize it, we see that W sine theta equals m times lambda, where again m is our set of integers. Not 0, because we know that at 0 we do get the bright central fringe. All of the distances are the same. But it can be plus or minus 1. So the plus simply means to one side of the central fringe. The minus means to the other side of the central fringe. And the bright fringes then occur approximately halfway between these dark fringes. It's not exactly halfway. There we have to worry about some of the trigonometry and the angles a little bit more, and we're not going to go through that particular detail. We're going to concentrate at this point on the locations of the dark fringes. So let's work out an example then. So let's say that we shine light with a wavelength of 532 nanometers onto a slit with width equal to, let's say, 80 micrometers. And again, we're not going to worry about physical distances because the screen distance is arbitrary. So what we want to know is at what angles do we see dark fringes. Okay, so we have our equation. W sine theta dark is equal to m times lambda. And we can take our first dark fringe that is given to us by the value of m equals 1, and for this case we'll just take plus 1. So if we plug in our values and solve for theta, we see that we get an angle of 0.381 degrees. For the second dark fringe, we plug in m is plus 2, and we get 0.762 degrees. So then we can also ask how wide is the central bright fringe. And we know that its width is 2 times theta dark 1. Again, because it's symmetric, these two dark fringes occur at the same angle on either side of the bright fringe. And we could just multiply that theta dark 1 times 2, or we can also go through and use our original equation for finding that, 2 times lambda over W. We can do 530 nanometers, and if we convert our slit width of 8 micrometers into nanometers so that the units cancel out appropriately, we get 80,000 nanometers. Sorry, I wrote that wrong, didn't I? My apologies. This should be 80 micrometers, not 8. Then we get 80,000 nanometers. That gives us an angle of 0.0133, and remember this is in radians, and if we convert from radians to degrees, we get 0.762 degrees, which is in fact twice what we had up here. So that equals 2 times our theta dark 1. And we can go a step farther, say those are our angular sizes, but if we have a screen, and the screen is set up 10 meters away, where are these features located? So in that case, we can find the Y positions of the dark fringes. So Y dark 1 and if we work out the trig, it's just L times the tangent of that angle for the position of the dark fringe. So it's located 6.65 centimeters from the central bright fringe. We can do the same thing for the second dark fringe. And it's located then 13.3 centimeters away. Likewise, we can find the width of the central bright fringe and find that it is in fact 2 times that value. Okay, so that is one example of how we can use this. So let's try another example. And here we're going to look at a double slit with diffraction. So we worked out previously that a double slit gives us an interference pattern. We also worked out that a single slit due to diffraction gives us an interference pattern. If we look at both of those together, what we see is actually what we saw in class. We saw the laser shining through the double slit, and we saw a modulated pattern of the narrower interference fringes from the double slit and a broader pattern with the interference pattern from the single slit. So we're going to look at another set of slits just as we had with the previous exercise or example. Light with wavelength 532 nanometers, slids of width 80 micrometers, and now we're going to take two slits separated by 320 micrometers. So with this we're going to see the first dark fringe from the single slit, and it will line up in this case with one of the bright fringes from the double slit interference pattern. So we want to know which one it lines up with. So we have our equation for the diffraction due to the single slit, and the first dark fringe, and we want to look at the bright fringe from the double slit pattern. So there we have, we're going to include our M value, and we know that the wavelength here is the same, and we know that these angles are going to be the same because we said up here they line up, they're going to overlap. So sine theta dark 1 is equal to, in this case, our bright fringe. So if those two are equal, then we get our equation for the single slit, W sine theta dark 1 equals lambda, becomes sine theta dark 1 equals lambda over W, and d sine theta bright equals M lambda from that sine theta bright equals m lambda over d. So now we can set those two equal to one another. Lambda over w is equal to m lambda over d. And the wavelengths cancel out because they're equal to one another. And we can then solve for m, because m is what we're looking for. We want to know which bright fringe lines up with the first dark fringe. And m is d over w. (320 micrometers over 80 micrometers, and that is equal to 4. So the fourth bright fringe from the double slit pattern lines up with the first dark fringe from the single slit pattern. So in that way we combine our single slit diffraction with our double slit interference and see how those combine with one another. Okay, so we can then also think about how these differ with different wavelengths. So this is something we also looked at briefly in class on Wednesday with the green laser and the red laser. And what we see from our equation, w sine theta dark equals m lambda, that as the wavelength changes, then the location of those dark slits change as well. So here's a graphical representation of that. So we have blue light and red light, and this is not quite to scale, but it is schematic showing you that the first dark fringe for blue is going to occur inside of the first dark fringe for red because of that difference in wavelength. So red light has a longer wavelength, so as lambda increases, then this angle is going to increase as well. So we'll see different patterns for different wavelengths. So it turns out that while looking at these single slits and double slits is interesting, everything we've been looking at now have been essentially rectangular slits. Rectangular slits do come into play in some applications in research, but more often than that we encounter circular apertures. So instead of a rectangular slit, we have basically a circular hole, and the light passes through the circular hole. So for a circular opening, the first dark fringe occurs at 1.22 times lambda divided by d, where d here is the diameter of the aperture. So again, sine theta dark is equal to this value of 1.22. We're not going to derive where that number comes from, times the wavelength divided by the diameter of the aperture, not the radius, but the diameter of the aperture. And if we shine a laser through a small circular aperture, we see that instead of bright fringes lining up in lines, we see this circular pattern moving out. So here's our bright central fringe. Here is our first dark fringe, now in a circle all the way around. So now it isn't just symmetric from one side to the other as it was with the rectangular slits. Now it's symmetric all the way around. So we see this dark fringe in a circle, and then the next bright fringe, and outside of that, the next dark fringe, etc., moving outward. So it turns out this type of aperture is, as I said, much more important or occurs much more often in nature. Around us, camera lenses are circular apertures primarily. Our eyes are circular apertures. And telescope mirrors are circular apertures. So the telescope that I'm working on now is a large round mirror. So it behaves with the same kind of effect as our eyes, but on a larger scale. So we could even think about how that scales. So the diameter of the circular aperture of our eyes can change dramatically depending on the amount of light coming in, but typically it's on the order of a centimeter or less. The telescope that I'm using this week, the diameter of the mirror is 4 meters. So the telescope mirror is 4 meters across. So we can think about the difference in the location of that first dark fringe. And that becomes important because it's related to this idea that we call resolution. You've probably all heard the term resolution before, and talking about how well things are resolved. And we're not talking about resolving arguments here. We're actually talking about being able to distinguish separate objects. So, in order to tell that there are really two objects there, the objects have to be separated by some distance. If they're too close together, then our eyes simply can't detect them as two separate objects. And we use the Rayleigh criterion to define that resolution. So the Rayleigh criterion here takes our original equation, but now we're just using theta. We're really assuming here a small angle. So for the small angle formula, the sine of theta is really equal to theta for very small angles again. And we're simply using then this first dark fringe as the definition of resolution. So, in other words, if we're looking at something with our eyes, we can tell there are two objects there if they're separated by more than the angular position of the first dark fringe. So, if you think about a second image up here, and the center of this other bright central fringe is at least over here, the distance of this first dark fringe away, then we would be able to tell that there really are two separate objects there, and we could detect those. If they're closer than that, then we're simply not going to be able to detect them. So let's work out another example with this, and with circular apertures. So another example here is a microscope. So we're going to look at a microscope lens with a diameter of 25.0 millimeters. And we're going to view a sample through this microscope, and we're going to use yellow light. And we're going to take the wavelength of that yellow light to be 580 nanometers. So if we're looking at a sample through this microscope with yellow light, we would like to know what the smallest sample is that we can resolve. So we just take our Raleigh criterion here, minimum angle, (1.22), wavelength of 580 nanometers, and a diameter of 25 millimeters. Sorry, I wrote that in meters. So in this case, 2.83 times 10 to the minus 5 radians. Again, our angle here works out in radians, and that is 0.00162 degrees. So that is our angular resolution. We would like to know the physical size, so in order to do that we need to know how far the sample is from the lens. So we'll say in this case it's 10 millimeters below the lens. Then the physical size is and we can use the small angle formula here. Because, again, our angle is so small, the small angle formula works well. And if we plug our number in, then this in degrees has to be converted into radians. So if we divide by the number of degrees, multiply by the number of radians in a circle, we get that conversion. So for those of you, if you didn't recall that and wondered about how we've been doing those conversions the last few times, that's how we convert between degrees and radians. And the result there then is 2.83 times 10 to the minus 7 meters, or 0.283 micrometers. So that will give us the resolution limit, and this resolution limit of things like microscopes and telescopes, and even for our eye, is called the diffraction limit. Realistically, quite often we have to worry about other things. This would be the limit if the lens for the microscope, for example, were perfectly formed, didn't have any flaws in it. If there are flaws in the lens for the microscope or with telescopes, we have to worry about the atmosphere and blurring in the atmosphere. So we don't always reach what we call the diffraction limit as far as resolution goes. But it does give us the minimum resolution or minimum angular size for which something can be resolved using a circular aperture. Okay, so that gives us an example of the circular aperture. We're, again, remember, talking about diffraction here. Diffraction through a single slit is where we started, and we derived where the locations of the dark fringes were for those single slits. We also looked at an example of using or combining diffraction in the single slit along with the double slit interference. We talked about the width of the central fringe in that, and we talked about this circular aperture. So when I return after Easter on Monday, we will pick up with diffraction gratings, and we'll talk about how we use this concept of diffraction to really help us start to understand wavelengths, how spectrographs and spectroscopes work quite often, and what some of the other applications of these concepts are. So I will see you on the Monday after Easter. Again, if you have questions, feel free to send me an email and I'll respond as I can.